what we're going to move into now is talking about the compounds making up petroleum systems. And I'm going to start because what I told you is that you will always have water in your system. It will always be there in the pores of the rock, together with hopefully oil, maybe also gas. Then we have, very often, in almost all cases, we have some nitrogen, some carbon dioxide. If you're unlucky, you'll have some hydrogen sulfide. Unlucky because, one, it kills you. It kills if you breathe it. And two, it's expensive to remove it because you don't want to be sending around production of gas with H2S in it because it kills. So you have to extract it out, and it becomes an expensive processing. Okay. And then we have methane, sometimes written CH4. Okay. Which is basically a carbon atom with 4 hydrogens. Everybody, I'm sure, knows this. We refer to this as methane. And then we've got ethane, which has got a symbol of, it's like 2 carbon numbers, or 2 carbon atoms, and there has to be 4 bonds on each carbon atom, right? Okay. Now I'm going to stop drawing all the H's, so each one of these lines ends up in an H. So we've got 1, 2, 3, 4, 5, 6 hydrogen atoms. Call this ethane. And then the propane we just looked at is C3. And let's see how many hydrogens we've got. We chain them up like this, the carbons together. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Propane. And what you can see in common for these, and for a while more, is that these have the formula CnH2n plus 2. I think that works. The first one's got 1 carbon, 2 times 1 plus 2. Didn't work for that. Yeah, that gives us 4. 2 carbons, we've got 6, and so forth. So I think this is basically our formula for one class of the hydrocarbons. These are all our hydrocarbons. So let me I'm going to just refer to these. These are typically referred to as non-hydrocarbons. Obviously, H2O is a non-hydrocarbon, so it's kind of, but often we ignore the water component, and I'll talk about that here a little bit later, maybe tomorrow before we talk about it. But these are the non-hydrocarbons, and then these are all of our hydrocarbons we're going to be talking about now. These are what we're making money off of. And then we've got C4. Let's chain these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that rule works again. This is called butane. But it ends up that there are 2 butane molecules that we can create, both with the same formula. And the other one looks like this. Chain 3 together, and we'll put a C out like that. And then we'll do 1, 2, 3, 4, 5, 6, 7, 8, 9. See, we got the same formula, C4H10. And this is called an isomer. These are isomers, and this is another butane. But we refer to this as isobutane, and this is usually called normal or just butane. And the symbol we change, we write it N dash and I dash, like that. Now, it ends up that isobutane boils off a little earlier at a lower temperature than does normal butane. Okay, not much, but a little bit. So we typically, the order of these that we typically use and report in laboratory studies, they always report these components according to where they, at what temperature they boil off. They're kind of ordered in increasing boiling temperature at 1 atmosphere. So I think the ISO, we can just double check that because again, Curtis, it could be right, might be wrong. Let's see here. Butane. We got the normal boiling point. Can somebody make a 30 Fahrenheit? Should be able to remember that. ISO butane. Yeah, boiling off at 10 degrees Fahrenheit. So it's, it's less, right? Everybody follow? So it's boiling off at a lower temperature than the normal butane. So that's why it's usually listed first. So I'm going to do that using my lasso. I'm just going to, I'll take this one here, move it down. There. And I'll lasso them both then. Like that. Okay. And we got the same kind of thing for C5, but you actually get even more different combinations of isomers that you can have. I'm just going to list them. I'm not going to go through all that. Normal C5. These are the two most common of the 5 compound carbon compounds. We've got those. Those are pentanes, iso and normal pentane. And then we start getting 6 carbon numbers, and you can start getting a lot more different configurations. I'm just going to write down normal C6. And then you've got a few of the isomers with straight chain, kind of straight chain. They're mainly the straight chain, maybe 5 carbons together, 1 off, and so forth. You got isomers with kind of straight chains. These are alkanes, I think. I don't know the names. You got iso C6 and normal C6, and then you've got some other ones. But another compound is the very important compound that comes in to petroleum systems is, and the formula here would be C5, according to H, these would both have C5, H12. These would have C6, H14, is that correct? But then we get a compound that we refer to as benzene. And this has the symbol C6H6. And here the carbons are double bonded, single bonded, double bonded, single bonded. Let's see, did I get this right? And then another one here, double bonded, single bonded. You see, they all have 4. Well, you need to add some here. On each one of these carbons, we've got a hydrogen. each carbon has to have 4 bonds, and it looks like this. So it's called a cyclic because it's connected in a ring compound, sometimes referred to as a ring compound, benzene ring. Okay, and this has very different properties than does all of these C6, these alkanes. Okay, very different properties. First of all, I think benzene is probably causes cancer if you get a lot of it around you, and it's not good to be around. But the benzene compound, the 6 carbon numbers and these 6, the way it's put together here, you find this in different petroleum reservoir systems, and it has very different properties. So one of the properties that's very different is, for example, the density is much higher than the density of our, for example, normal C6. Same number of carbon numbers, but it's a lot denser. So let's take a look at that. Let's look up the densities, just hexane. Density 655 kilograms per cubic meter. So we'll put this 655 kilograms per cubic meter, and make sure Curtis is not selling you a line. Benzene 875 kilograms per cubic meter. Okay, so those density properties and really all the other properties are quite different, and and the benzene is all compounds that contain the benzene ring are referred to as aromatics. A single benzene compound, and then you may have a chain of other carbon numbers in more of a straight chain beyond that.
Why is it denser?
Well, I'm not a chemist, so it must have something to do with the geometry of these carbon numbers being in a ring, being more compact than a longer chain. I really don't know. I mean, it's maybe the molecules can be, in a sense, closer to each other because of the configuration. They can pack more tightly. I don't know really the reasons for that.
Something like this double bonds.
Yeah.
Create some 6 plane of symmetry in the molecules.
Okay.
So they can pack.
So they can pack them, the molecules themselves, the compounds can pack closer together. So, yeah. Thanks. Okay. And then you've got so aromatics, and then what these straight chain alkanes are also referred sometimes to as paraffins. Okay, alkanes or paraffins. It's mainly a straight chain without any aromatic rings. So the type of chemical compound, hydrocarbon, there's 2 classes that we've now looked at. One is paraffin, one is aromatic, and they're at the extremes of properties for a given number of carbon numbers. Okay. So you've got, we can just kind of classify. You got paraffins or alkanes, and then you got aromatics, And all of the properties from density to whatever solubility in water, whatever, are going to be very different for these compounds, given the same number of carbon atoms in a molecule. Okay. And in between, there's, I think, naphthenes. I think naphthenes have two of these benzene rings together, and then otherwise it's kind of like more straight chain. But they kind of fall in between the two extremes. So often we refer to, these are the kind of the chemical makeup or character of hydrocarbons, in terms of, is it more paraffinic, do we have more straight chain, do we have more aromatics, and the naphthenes kind of also come in. So sometimes this is referred to as a P&A. Sometimes they measure of a given carbon number how much of the compounds are paraffinic, how much are naphthenic, and how much are aromatic. Sometimes it's quantified. So you can have really, really large differences in densities and in viscosities, for example. And one thing that's known in the industry, particularly refining, is that if you look at single carbon number, for example, starting at C7, C6, C7, maybe C10, C20, C30, and so forth. If you look at the relative percentage of, for example, paraffins, then you'll often see a variation in this. And often it kind of goes down. I mean, general trends, it might go up, and then it might go like that, and then you might have some. So you've got a variation in how much paraffin and aromatic you have. So because this has such a huge effect on both density and viscosity, you would not necessarily expect to have purely monotonic density versus carbon number or viscosity versus carbon number because of this variation in chemical makeup with carbon number. So both the density and viscosity might generally be increasing as you go to higher carbon numbers, but they don't necessarily have to be monotonic. There can be wiggles following the chemical makeup variations that you often see. And there's a in the book there's a nice equation. There's some figures and equations that show this. I'll try to find it for viscosity first. Yeah. Okay. Okay, so what this figure is showing is it's using the API density unit here, so that you basically have a density of a liquid increasing in this way. So this might be in kilograms per cubic meter. I'm going to do a kind of an approximate conversion. It might be on the level of 700, and then it's approaching 1,000 here. Okay? And so in a sense, the single carbon number would be kind of going from like C7-ish to C30-ish, maybe heavier than that, moving in the left direction. And so for a particular carbon number or oil with a given density, you can see that this characterization factor, it's a means to identify relative paraffinicity. So this would be relative paraffinic, this would be relative aromatic, okay? And you can see that the viscosity of a paraffinic component is in this case about 1 centipoise, whereas the aromatic compound has 0.35 centipoise. It's much less viscous. Same density, might be 750 kilograms per cubic meter. Same density, same carbon number, but very different viscosities. Let's check that for benzene and C6 just to see that's the case. I don't know. Again, I could be wrong, but benzene, does it give viscosity here? We'll have to go. We need a little more viscosity. Does anybody see a viscosity here?
Right.
Yep.
Where?
It's on the right, under properties, going down.
There we go. 0.65. Can y'all remember that? And then we'll go back to hexane. Well, it's in a different unit.
And we
0.3.
so almost 300 centimeters.
Well, but that would be, this is micropascal, so this is 0.3 centipoise. I think we have to compare it maybe with heptane, because it's benzene and heptane are usually the ones that are compared. But for the heavier components, this is generally the trend that you have these. So if we go to heavier and heavier components, you can just see that like the aromatic viscosity is still staying, it's just short of 2 centipoise, and the viscosity of a more paraffinic component is 15 centipoise. So the ratio is 7 here. Here it's a ratio of 3. So the heavier the component, the bigger the contrast you get between paraffinic and aromatic components. And in terms of density, I can show you the same kind of plot, but it'll be from a different chapter 5. There's a figure there showing how density varies for, it's probably the best. This kind of gives it in terms of aromaticities, which is the opposite. So here, this is more paraffinic, or aromatic, and again, if we go in for, well, this would be probably C6. This is the first benzene, and this is like benzene density we saw, and this was the density of normal, probably normal C6. So for a given carbon number, you can see there's really a huge variation in the density. So if in fact it's true that the relative paraffinicity varies with carbon number, which is well established from the refining industry, then you would expect to at least see not completely smooth and monotonic behavior of both density and viscosity for increasing heavier and heavier components. And I think I know time is out, but there's a Norwegian student who did his thesis with me in 1979 and 80. I think his kids have already come through the program here. Sigve Holand in Stavanger. I think he's the vice president now. And he did characterization of oils and made some measurements, and I think those are referenced in the book here. And he actually showed the variation of this paraphenicity with carbon number. I'm not sure if this was the... Okay, so you can, this is actually not, I'm not sure if this is his data or not, but what you can see here is the higher this KW number, the more paraffinic. So you can kind of see that it's decreasing, starts increasing, reaches a maximum around C12, decreases again, starts increasing, and has this variation. So this is a fairly typical characteristic you see in crude oils. Okay, so we'll stop there, and tomorrow what we're going to do is talk about phase equilibrium that also includes water, the water phase, and then we'll talk about when it's important, when it's not important, and then we'll find that for the most part we disregard the effect of the water phase on gas oil phase equilibrium. But we'll talk about it first and why we can ignore it in some cases.